as we start talking about physics, and especially in one dimension, we need to start by defining what is motion. Specifically, what do we mean by one-dimensional motion, so 1D motion? So first, what is the simplest form of motion? Simplest form of motion is straight line or one-dimensional motion, hence 1D motion in the first unit. Straight line motion is also called linear motion. So linear meaning line, so linear motion, motion in a line. So let's talk about what we mean by linear motion with a quick concept check. You point a camera at a runner and take a series of pictures and look at those pictures. How do you know she is moving? Well, what a lot of people would probably say is if you're looking at a series of pictures, then you'll see her hands and her arms and her legs and her feet moving and making that motion that we think of as running. So her arms are moving forward in circles, her legs are moving forward in circles, and just looking at her, you can tell that she's running based on the motion of her limbs. Well, you could also look at it from, what about in the background? So if you were to look at the background, depending on how fast she's running, you can always see either like the background is blurred, which means that she is moving quickly in comparison to the background, or if she's, say, doing a very slow run or a jog, you would see that she is moving relative to the background. So in one picture, she might be in front of this tree. In the next picture, she might be in front of this tree. In this one, she might be in front of this bench and things like that. And so we can tell motion based on relative motion. So motion is relative to other objects. You can't just look at motion on its own. You're always going to be looking at it relative to something. For us in physics, we're going to do this considered relative to Earth or relative to the ground. If someone were to ask you, how fast are you moving right now? Well, if you're sitting in a chair, your thought would be, I'm not moving at all. I'm moving a speed of 0. But depending on your point of view, your relative point of reference, you might be moving. If you were to look at it from outside of the Earth, you would be moving at the speed of the Earth. If you were looking from outside of the solar system, not only would you be moving the speed of the Earth spinning, but also the speed of the Earth going around the sun. So this is why figuring out what that relative point is extremely important. For labs, for practice problems, for anything that we're going to be doing in the classroom, your relative point is going to be the ground or the Earth. For labs, of course, it'll probably be the tabletops or the ground, depending on where we are using our surface to collect our data. So, next thing we need to talk about is the difference between vectors and scalars. And again, this is all based on relatives. So first, a scalar is a measurement that has an amount but no direction. An amount but no direction. And what we mean by amount is it's a number. Amount of money is how much money you have. It's a number like $20 or $100. So an amount is just a number and a unit. So in the case of money, the number would be 20, the unit would be dollars. So this is just a number. Another word you might see when it comes to amount is magnitude. Do not get confused with this word. Magnitude is just the technical term for a number with a unit. That is it. Some examples of scalars: temperature, which has a unit of degrees Celsius. So what is the temperature outside? Well, it would be 20 degrees Celsius. 0 degrees Celsius. It's just a number and a unit. Mass. Mass has a unit of kilograms. Speed, meters per second. This could also be a different unit if you're, say, driving down the road in America, then speed might be in miles per hour. If you go up to Canada or anywhere else in the world, it might also be in kilometers per hour. But nonetheless, it's still a number with a unit. And of course, we have distance. Distance is measured in meters, kilometers, centimeters, millimeters, things like that. But again, still a number and a unit. So a car is traveling 2 kilometers. Which way? Well, if it's a scalar quantity, we don't care about the which way. All we care about is that it's going 2 kilometers. So if someone were to ask you, how far away are you from the school? You know, how far do you have to go in order to get to school every day? You might say, oh, I'm a mile away from the school. It's not telling us anything other than a number with a unit. We don't know if it's towards Arcado, if it's towards Five Forks. It doesn't matter. All we care about is that number. Now, what if we do care about which way we go? That's where we bring in a vector quantity. A vector quantity is a measurement that has an amount and a direction. So amount and direction. So for a vector, you would have this number in a unit, so say 2 kilometers, and then the direction would be towards Arcado, or 2 kilometers towards Five Forks, or something like that. So there has to be some sort of directional component. Some examples of those: velocity. Notice this is in meters per second as well, just like speed. So things can have the same unit, but be different in terms of scalar and vector. The difference is right here. Direction. Vectors have direction. Force is also a vector. Force is just a push or a pull. And so you are always going to be applying a force in a certain direction. You're going to be pushing it to the left, pushing it to the right, pulling it down the hallway. There's always going to be some sort of direction involved. And since there is direction, we're going to be drawing vectors with an arrow. So let's go a little bit more into vectors because these are a little more specific. So first, vectors. The length of the arrow indicates the magnitude. And again, don't get mixed up with this word. It's just the number and the unit. It's the amount. So let's say you have an arrow this big and an arrow this big. This one has a much smaller amount than this one does. So you could imagine, say, looking at a map, right? So if you're looking at a map, this would be a house that's much closer versus this one is much further. So the length of the arrow indicates the magnitude, just the number and its unit. So the first type of unit we need to talk about is a fundamental unit. Fundamental, by definition, just means the beginning, the principle, the initial. Fundamental, in this case, for units, means 1 unit. So if you see kilograms, that's 1 unit. Meters is 1 unit. Seconds is 1 unit. These are ones that stand alone. Fundamental units stand alone. A derived unit is one that is made up of more than 1 unit. And it makes sense because the word derived means to create, to build, to construct. And so your unit for a derived unit will have more than 1. So examples: meters per second, meters/seconds. You have meters and you have seconds, 2 different units. A newton, which we'll get to later in the semester, is a unit of force. But to create a newton, even though it is technically 1 unit, is not a unit by itself. To create a newton, we have to have a kilogram, a meter, and then seconds squared. 1 newton is the same as this, kilogram meter per second squared. Looking at it this way, you can tell it's derived because you can see multiple units. All right, so now let's talk about the direction, because for vectors, vectors have magnitude, or an amount, and a direction. Well, this one makes sense. The direction of the arrow indicates the direction of the vector quantity. So in my two arrows that I had up here talking about magnitude, they both have the same direction. If instead we had an arrow going this way and an arrow going this way, we would now have different directions because they're pointing different ways. So here are a couple of examples here. We have 5 meters going east, and based on our cardinal directions here, north, south, east, and west, east would be pointing to the right. We have 2 meters going north. Notice the arrow is shorter, so 2 meters is a shorter arrow than 5 meters, and it's pointing up for the cardinal direction north. When you're writing these down, there are a few ways that you can indicate direction of a vector quantity. So one is what we were just saying, north, south, east, and west. So north, south, east, and west are your cardinal directions. We can also say up or down. So if you were talking about, say, different floors, so if you were in a building, for example, you would say that it would be upstairs versus downstairs. That would be a direction. Up and down are your direction. We also have this one, which is positive and negative. Positive can mean a couple of things. It can mean forward, or it could also mean up, depending on what orientation we're looking at. Negative could mean backwards or down. So positive and negative can also indicate a direction, forward and up, backwards or down. Now, this next one in degrees, we did talk about temperature. I'm going to come back to that in just a second. Degrees here means an angle. So make sure to make a note of that. This is an angle measurement. So we're going 5 meters, 30 degrees north of east. We're going 10 meters per second at an angle of 40 degrees. It's an angle measurement for degrees in terms of direction. Now I'm going to erase some of this and talk about the one exception to this positive, negative, and degrees rule. So here, we'll put this as positive, negative, exception. And that would be temperature. Temperature is based on a scale. This is just a number. Does not matter if it's positive or negative. Just a number. So if you have a temperature of positive 2 degrees C, it's pretty cold, but it's above freezing. That's what a positive degree C means. This positive does not mean that it's a forward temperature. It's just based on the scale. If we have, say, negative 2 degrees Celsius, this does not mean it's going backwards. This does not mean it's going down. This is just a number. Negative degrees in terms of temperature is still scalar. This is the one exception to that rule. Positive and negative, if it is a temperature, is always a scalar no matter what. Temperature is a scalar quantity. So, why is this stuff important? Why do we care about vectors versus scalars? Well, it's because of precision. If, again, someone said, how do I get to your house from Parkview? And you were to say, oh, you go a mile down the road. Well, which way? Which way a mile down the road? Do you go down Five Forks? Do you go up towards Arcado? Do you go down Miller? What do you do? So precision is extremely important. This is that distinction between the actual path and shortest path from A to B. And we'll talk more about this one when we get to distance and displacement. And in motion and forces, it's important to talk about which direction you are going. It makes a big difference if you are pushing something to the left or to the right when we're talking about friction, when we're talking about inclines and things like that. It's very important to know the direction that you are going. So it's very important to make sure that you know what a vector quantity implies. It implies that there is a number as well as a direction. So let's do a few examples. So example number 1 says 10 meters per second, and this N stands for north. So we have 10 meters per second north. We have a magnitude, so that's our magnitude. And we have direction. And so this is a vector. Number 2, we have 8 kilograms. Kilograms is our unit. Notice that there's no direction. There's no positive or negative here. There's no north, south, east, or west. And there's no angle measurement. Plus, this is mass. Kilograms measures mass. Mass is always scalar. And then number 3, we have negative 15 meters or kilometers per hour. So we have 15 kilometers per hour, which is negative. That negative is implying either down or backwards, which is a direction. So this one is a vector. That negative is a direction. So again, going back with our exception, why don't we make a number 4? So let's say for number 4, we've got negative 10 degrees Celsius. Degrees Celsius is temperature. Because this is negative, it doesn't matter. Since this is a temperature overall, no matter what, it is a scalar. That is our exception to that positive-negative rule. Temperature is always a scalar.